Hi, my name is Muchibi Juma. I'm a student at Deja University and I'm doing my bachelor's in software engineering and I'm a third year.
Hey everyone, I'm Selonyoji Marvin, a third year student at Deja University, and today, together with my colleague, we are going to be talking about our smart water tank level monitoring and pump control system. This is an embedded system.
Without wasting time, I'll be starting off with the project. I'll really run into the project. So here we have the problem statement. Manual water level monitoring is unreliable and inefficient. That is if it is done by people. That is why it is called manual. And usually the tanks run dry before anyone notices, or there is overflow when the tank fills and there is no one there. So like we all know that people usually forget to check, or at times notice too late when the tank is already overflowing, like water is already overflowing, so there is, in other words, wastage of resources. So our system solves this problem by automatically monitoring the water level and controlling the system using a pump indicator. In other words, no human intervention is required. So quickly, let me walk you through the components of this circuit. First, we have the Arduino Uno, Arduino Uno controller, and it is basically the brain of the system. Think of it as the CPU of a computer. It runs the logic, reads the sensor data, and also controls every output component. And then next we have the HCSR04 ultrasonic sensor, which is mounted at the top of the tank, and it fires, or it sends sound waves down and measures how long they take to bounce back. That way it gets to know the water level. So the more the distance means the less the water in the tank. Then we have the 4 LEDs, the LED lights, which are of different color. Now these LEDs are of different color. That is red, which signals that the water level is critically low. There is yellow for a medium water level, and then green when the water level is full. There is also the blue LED color, which signals the pump indicator. We also have the buzzer that sounds an alert. It's like an alarm in the system when the water reaches the critical level. That is when the red LED turns on, and then the buzzer will also light blue. Then lastly, in this circuit we have the 220 ohm power resistor for each LED light. And these resistors they protect the Arduino pins from excess current. And
Now, since my colleague has gone through all the components for our system, let's see why each component was selected for this specific system, why we chose the sensor, the buzzer, the LED, the ohm resistors, and also breadboard and an Arduino for our brain for the system. Let me walk you through every connection in this circuit and explain why each one is made the way it is, as you can see here. Starting with power, the 5V and the GND connections. The Arduino has a 5V pin and a GND pin in the power section here. This power section of ours, as you can see it. This is the 5V, and then these two GND pins. These are power supply rails for our components. They supply power to all our components. Every component in this circuit needs power to operate. So we run a 5V wire, this wire here. We run this wire to power the HCSR04 sensor. So this is the wire that we are running to power this. It's connected to the VCC, and a GND wire, this wire here, that connects to the breadboard and acts as a common ground reference for everything: the sensor, The sensor, it's like you see here, you have the sensor here. It is connected to this line. We have all the red lights are connecting to this light as well, including our buzzer. All of them are connecting to this ground wire that is from the Arduino board, from our power section. Without a common ground, no current can flow and nothing works. If you try to eliminate this line here, nothing will be able to work in your simulation. Now proceeding to the HC SR04 ultrasonic sensor. It has 4 pins. The VCC here, this VCC. It has the G, like I mentioned, it has the VCC pin, it has the GND, it has the trig and echo pins. So our sensor here has 4 pins, which are connected to the breadboard and the Arduino board as well, for power and sending signals. VCC connects to Arduino 5V, to this VCC here. It connects to our Arduino 5V. Then GND connects to the common ground. We just established our GND here pin connects to the ground that we established earlier. Then the trig connects to the Arduino pin 9. This trig here, it connects to Arduino pin 9, as you can see. The trig pin, it is the trigger pin. When the Arduino pulls it high for 10 milliseconds, the sensor fires an ultrasonic burst. We chose pin 9 because it is a standard digital output pin. It can go high and low on command. The Arduino is in full control of when the sensor fires. Then we have the echo pin. The echo pin connects to Arduino pin 10. Echo is the response pin. It goes high the moment the sensor fires and goes low the moment the sound returns. The Arduino measures how long echo stays high using the pulsing function. The duration is multiplied by 0.034 and divided by 2. This gives us distance in centimeters. We divide by 2 because sound travels to the object and back, so we only want one way. Pin 10 is configured as input because the Arduino is reading from it, not controlling it. Now the resistors are YV LED and buzzer has 1. The Arduino's digital pins output 5 volts when high. An LED has very low resistance on its own. If you connect it directly, too much current flows through it and through the Arduino's pin. The maximum safe current per Arduino pin is 40 milliamps. An LED without a resistor can pull 75 milliamps or more, which is exactly the error we saw during the testing, was our board was actually catching fire during our simulation, which was strange. The 220 ohm resistor limits current to approximately 18 milliamps, well within the safe range, bright enough to see clearly. So yeah, you'll be seeing the lights when we are testing or when you're simulating. Every LED gets its own resistor. The buzzer also gets one for the same reason, to protect pin 6 from excess current draw. Now let's focus on our red LED light here, which is connected on pin 2 on our Arduino board. The red wire from this red wire here from the Arduino pin 2 goes into the breadboard. Then through a 220 ohm resistor, this resistor here, then it is then into the anode, which is our longer leg here, this leg here for our LED light. Then the cathode, which is the shorter leg, connects to this shorter leg here. It is connecting to the common GND that we mentioned earlier. Pin 2 is configured as output. When the code writes high to pin 2, current flows through the resistor, through the LED, and output to the GND. The LED light then lights up. When low is written, no current flows and it goes off. The red LED is our critical and low level indicator. Now let's focus on our yellow LED, which is on pin 3. This yellow LED light, this yellow LED here is connected on pin 3. It follows the same exact pattern for the red LED. Pin 3 output, where into breadboard, it goes through a 220 ohm resistor into the cathode of the yellow LED, cathode to the common GND. The yellow light, it lights up at medium water level. Same physical connection pattern, different pin, different meaning in the code. Now let's focus on the green LED, which is on pin 4, which the green LED is connected on pin 4. Same pattern again, pin 4 output, resistor in series, anode connected, cathode to our cathode here is connected to the common GND. Green makes the tank, when the green light is lit, it means that the tank is full. When green is on, the pump is off, the system is at rest, since our water tank will be always full when the green light is lit. Now moving forward to the blue LED, which is on pin 5, this pin 5 here. This is the pump indicator. Same connection pattern, pin 5 output, resistor, anode, cathode to the common GND. The blue LED resistor represents the pump motor. In a real system, pin 5 would connect to a relay or motor driver to switch an actual pump on and off. In simulation, the blue LED lighting up means the pump is running. It turns on at medium level and stays on through low and critical, only switching off when the tank is full.
So, starting off with some definitions, pin 9 and 10 are for the ultrasonic sensor, trigger and echo. Then pins 2, 3 and 4 are the LEDs, that is red, yellow and green respectively. Yeah, I'm on from line 1 to line 7. Then pin 5 controls the pump, and pin 6 is for the buzzer. This setup helps us visually and physically monitor the tank. Yes. So now quickly moving down to the setup function. Under this function we configure all the pins, yeah, like you see here from void, this setup function, yeah. And trig is output because it sends signals, and echo is input because it receives signals. And all LEDs, as in the LEDs, the pump and the buzzer, are outputs. And we start the serial communication at speed 9600. This the very last part of that portion of the code, 9600 baud. Okay, those are units that measure speed, yeah. and so we can monitor everything from the serial monitor. This is okay. 9600 is the speed at which the Arduino board communicates with any other device. Yeah. And then coming down to it's the distance function, and it is the get distance, like we see. We have it is the function, the get distance. We send a short pulse from the trig pin. Then the ultrasonic sound sensor, the ultrasonic sensor sends sound waves, yes, and then these sound waves bounce off the water surface and return. Then we measure how long it takes using the pulse in function. Yeah, this one here. That is how we measure how long it takes. Then we convert that time into distance using the formula. Distance is equal to duration time multiplied by this formula here. Yeah. Duration multiplied by 0.034 divided by 2. Yeah. I want you to keep in mind that 0.034 is the speed of sound. Yeah. Yes. So, following through the code, we come to the logical part of it. Yes, the main logic. Let me put it that way. Now, inside the loop, the system keeps checking the distance continuously. First, we reset all the LEDs, all the LEDs off. That is why you see low everything. Yeah, yellow, the green, the red. Yes. Then we use conditions to determine the water level. Coming down, we see an if statement. Yeah, from the if statement, that is if the distance is greater than 250, then that means the water level is very low, and so the red turns on, pump on, and the buzzer on, like my colleague will explain. I'm sure, like my colleague will explain will illustrate with the using the simulator. Yes. Then we print critical, that is very low. Yeah, so if if that is right, then we see to it that it is supposed to print this. Yeah, sorry, I'm having a problem with my touchpad here. Then else if it is not the case, if the distance is above 150, that means the water is low but not critical. That is why it's an if else. I don't want to do a lot of explaining, because I best believe we all at this level we're familiar with the C programming. Okay, so this is C++, but it's not so different from the other original C that we know. So there is else if, then else, which is the should I say the last option, that is if none of those conditions are true, then that means the tank is full. Yeah, so if none of those conditions are true, that means the tank is full, so it will have to output that. So it will instruct, so the system will automatically stop the pump when the tank is full. Then we add a small delay of 500 milliseconds to make the readings stable and avoid unnecessary rapid switching. Yeah. Yes, so basically this system automates water monitoring and prevents overflow or dry tanks. It is useful for homes, farms, and even industrial setups. Yes, in our daily life, because human intervention at times is inefficient and unreliable, because we as people, we can be lazy and yeah.
Our ultrasonic sensor is going to be mounted at the top of the water tank, so it will be measuring the distance between the sensor or the top of the tank and the water level. So when the distance is longer, it will indicate that the water level is at a critical state, low state. Maybe when the distance is medium, it could be at the medium state, or the distance is less than 80 centimeters, the water level will be at a full state. Let's dive into the system's behavior to see what distance triggers what output. When the distance is greater than 250 centimeters, our water level will be critical, and the red LED light will be on to signal the critical condition at hand. The yellow LED light will be off because it's used for the medium level. The green LED light will also be off at this point, and the pump LED will be on because whenever the system detects that the water is at a critical level, the pump will be always activated to make sure that the tank does not go empty, and the buzzer will be on, like notifying the user that the water level is critical and maybe they need to stop the consumption and focus on refilling using the pump. When the distance is between 150 to 250 centimeters, the water level will be low. The red light will be on, the yellow light will be off, so as the green light will also be off, and the pump LED light will be on. This is because our LED light works in a way, for the pump will be working in a way such that as long as the water is not full, the pump will always be on. As you can see here, the pump is only off when the distance is less than 80 centimeters, which is signaling the full water level. When the distance is between 80 and 150 centimeters, our water level will be deemed medium. The this red light here will be off, the red. Then the yellow one will be on to signal that the water level is at the medium level, and the green light will be off. The pump will be on. This is because, like I explained earlier, the pump will always be on as long as the water level is not full. The buzzer will also be off. The buzzer only activates when the water reaches the critical level. When the water level is less than 80 centimeters, if it's a short distance, so we will assume that the water level is full. This can be adjusted in our code, but since most water tanks leave some distance from the top to where our sensor will be mounted, so we'll be starting at 80 centimeters. As long as the distance is less than 80 centimeters, the water level will be full for the tank. The red light will be off, so as the yellow. The green light will be on to signal the water level being full. This is the only time our pump will be off, because the water will be full. If the pump is on, then the water will just overflow, and the buzzer will also be off at this point. Now let me demonstrate the system running in Tinkercad live. I'll walk through each water level state one by one, showing exactly what the system detects, what it displays, and what the serial monitor confirms. On the right we have our serial monitor, on the left we have the setup. And before I begin, the setup is on the left. You can see the Arduino Uno connected to the breadboard with the HC SR04 ultrasonic sensor mounted at the top. The four LEDs are aligned on the right side of the breadboard: red, yellow, green, and blue, each with its own resistor. The buzzer is below them. All connections are complete, and the code is loaded. When I click start simulation over here, and I click this, Arduino begins executing the loop, reading distance from the sensor every 500 milliseconds and responding accordingly. The simulation is now running. To control the water level, I click on our sensor here. Now you can see the distance, the distance slider. The slider represents the distance from the sensor to the water surface. Remember, since the sensor sits at the top of the tank, facing downwards, a large distance means the tank is nearly empty, and a small distance means the tank is full. So stage 1, our first state, we are going to be testing the critical level state. This will be achieved by our first do what? Test this, then we see the reaction, then after we can draw conclusions. By dragging this slider to over 250 centimeters, now we are at over 250, we are at 222, 227, over 250. buzzer is, everything that is running at this point. We have the blue light which is indicating the water pump, the red light for critical levels, and the serial monitor is also telling the cell story. Based on what we have observed, the red light lights up, indicating critical water level. The blue LED also lights up. The pump has activated automatically. Trying to refill the tank, because that is, this blue LED light represents the actual water pump that is responsible for pumping water into the tank. So when it is activated, it means the pump is activated to start pumping water into the tank. And you can also hear the buzzer sounding. This is the alert telling whoever is responsible that the tank needs urgent attention. Now look at the serial monitor at the bottom of the screen. It is printing critical, water very low, power on, alert on, every 500 milliseconds. The system confirms its current, the system is currently confirming its current state. This is real-time monitoring. The system never stops watching. This is the most urgent state. Pump is running, buzzer is sounding, the red LED is on, everything is telling you act now. Moving on to state 2, which is low level. This is, we can observe this around 200 centimeters, around the 200 centimeter range, as you can see here. The tank still has very little water, but it is no longer at the critical level. Still, notice what you can notice what is changing at the moment. The red LED stays on and the blue pump LED stays on. The pump is still running, but the buzzer has gone silent. As you can see, the buzzer is no longer active. The system has determined that while the situation is still serious, it no longer requires an alarm. The pump is handling it. The serial monitor now reads low, water low, power on. The system has smoothly transitioned states without any flickering or confusion, because we reset all LEDs at the start of every loop cycle before applying the new state. Moving on to the state 3, which is the medium level. We shall be able to see this around 100 centimeters. 100, yeah. When you get to that range, bring it closer still, around 100 centimeters. The tank is now at medium level. Water is present but not yet sufficient. Watch the LEDs. The red LED turns off, the yellow LED turns on. Medium level confirmed. The blue pump LED is still on. This is an important design decision. The pump does not wait until the tank is critically low to start working. It activates here at medium. So by doing so, the time you check on the system, the tank is likely already refilling and will never reach critical. So your monitor reads medium, filling, pump on. The system is calm, no alarm, pump running, everything is under control. Moving on to state 4, which is the full tank. This happens below 80 centimeters. If we come here, we get below 80 centimeters. Now, if I bring the slider below 80 centimeters, the sensor is now very close to the water surface, meaning the tank is full. Look at all the LEDs. The LEDs are red goes off, yellow goes off, green lights up. Tank is full, and the blue pump LED goes off. The pump has automatically switched off. There's no point running a pump into a full tank. The buzzer remains silent. So your monitor reads full, tank full. pump off. Mission accomplished. The system filling the tank and stopped, or it stopped itself. No human intervention at any point. This was the whole idea. Okay, let me cycle through the states one more time. From a full tank to a critical condition, or to the critical state. Now our tank is full. When the distance grows bigger, we eventually get to the medium state, where the water pump, the blue light is on and the yellow light is on. Moving further, we get to the red, or the low zone, or the low state, which is also like things are not yet worse because there's still some water in the. You can follow along with our serial monitor. Then as the water goes on and on reducing, then we reach our critical state. When we're pumping more water, the water is being pumped in, then the system adjusts to the low state again, then furthermore to the medium state, then furthermore to the full state. That is the complete simulation demonstration. The system correctly monitors water level in real time, activates the pump early at medium level to prevent the tank from ever running dry. Sounds an alert alarm only when the situation is truly critical, and shuts down the pump automatically when the tank is full. This embedded system this embedded system automation working exactly as designed. Sensor reads the processor decides output, then it is followed by the output or the responder. From the output responds